Good. The screen is shared. Okay, so yeah, so the purpose of this class to conduct this on a Saturday is I'm trying to just catch up on the portions because we're lagging a bit behind, and you need some of these concepts later in machine learning as well. Okay, so yesterday, just to give a quick recap, what we were doing was we showed the strong duality theorem. We proved strong duality for linear programs. Okay, and then as a consequence of strong duality, I showed you this, like, how you can use the dual as a certificate of optimality. And a further consequence of this is what was called complementary slackness. And we saw an example how you can, solve the dual to get the primal solutions, and you make use of this concept of complementary slackness here. Okay, so when I told you complementary slackness, yeah, I kind of got excited to quickly go into the problem and to show you an example. But there's one thing that kind of got hidden when I explained it. I mean, of course, we used it in the problem, which is that because of strong duality, you have the primal is this form, minimization of C transpose X subject to, AX greater than or equal to B, and this is the dual. Okay, and we had that as a strong duality says that at optimality, C transpose X is B transpose Y. So for X star, which is primal optimal, and Y star, which is dual optimal, you just write it here. So what we have is C transpose X star is equal to B transpose Y star, right? And the way we wrote the dual was the ways in which we wrote these multipliers ensured that these multipliers we had here for this problem. So we had B transpose Y star was less than or equal to X star transpose sorry, what is it? Y. Let me just write this in this manner. So Y star transpose AX star again, because this was the optimal, and this was also less than or equal to C transpose X star. I mean, so this is true for any X and Y, and in particular, this was true for the optimal solution. And since C transpose X star is equal to B transpose Y star, all these are going to just become equalities. So this is an equality, and this is also an equality. Okay, so yesterday we saw one implication of this. So from this side, the equality on this side, what we have is Y star transpose AX star minus B is equal to 0. Okay, or in other words, we had summation yi, so y star. So this is the ith term. So there are these y's correspond to the constraints of the primal. Okay, the constraints corresponding to these. So there are m equations. So here there are, the summation goes from I equals 1 to m. And this is as though you're seeing the inequalities, right? So this will be, let me just write it as a x star minus b, the ith term. So this is the ith inequality, and this product is equal to 0. And now since you have x star is feasible and y star is feasible for the dual, this is greater than or equal to 0. And this part is also greater than 0. So it turned out that y star times ax star minus b, the ith term, each of these terms in the summation are also 0. Okay. Now another thing is you can do the same thing for this part, for this side inequality. And in fact, we kind of used that result in the problem, but I didn't explicitly mention it. So I thought it's just useful to state it out. So here, the same thing, if you do, what you're going to get is, so x star transpose. So I'm just writing it as x star transpose C minus A transpose Y star. Okay, it's the same thing. I'm just moving this to this side and writing it in a flipped manner. Okay, so this is also equal to 0 because finally C transpose X star is equal to Y star transpose A X star. Okay, so by the same way, here also you're going to get, so here this is i's from 1 to n. So this is for each of the variables in the primal space. What you're going to have is xi star times C minus A transpose y star, and this is the ith term, ith constraint of the dual, and this is equal to 0. Okay, so again x star and y star are primal and dual feasible respectively, so this is greater than 0, and this part is also greater than 0, so you must have that each of these products are equal to 0. That's the only way this overall summation can be equal to 0. Okay, so that means xi star times c minus a transpose y star, the ith term. So the ith inequality of the dual times xi star, the corresponding dual variable of the dual, so which is the primal variable. This is equal to 0, and this is for all for all the variables, and this is for all the constraints. Okay, so actually both these, so these are kind of, okay, it's symmetric because those are dual forms. These come as results for the dual forms. So both these conditions form the complementary slackness conditions. Okay, so both these are referred to as the complementary slackness conditions. Okay, so now I mentioned to you about this certificate of optimality. Okay, so another way to see is that you have these primal and dual optimal points. Now, instead of saying strong duality in a direct manner, another certificate is that one, you have a primal feasible point, primal feasible x star, and two is a dual feasible y star. Okay, and instead of saying strong duality, you can also say complementary slackness. Okay, so complementary slackness holds for the pair x star y star. Okay, so if this happen, so all these three together also imply that x star is optimal for the primal and y star is optimal for the dual. Okay, so it's both ways. So if strong, I mean, since strong duality holds, you have complementary slackness holds. Now if complementary slackness holds, these points are also optimal, so it's both ways. So this is also another certificate of optimality. Okay, and it's actually this idea that many of these algorithms use. So we saw simplex method, which is actually, it is a primal method in the sense that at every step you are maintaining primal feasibility. That we have seen, that is quite obviously we have seen the way the steps were done ensured that at every point the new basic feasibles, the solution you got was feasible, and it turns out that it also maintains complementary slackness. And the final step where you check whether the reduced cost coefficients are greater than 0, right? You stop at that point. So it turns out that that is ensuring that the dual is also feasible. Okay, so we're not going to go into those details of the algorithm for want of time, and I want to do some other portions as well. Okay, so but the very basic simplex method that we saw, it was trying to ultimately come to arrive at these three conditions. Okay, now there are other variants, like there's this algorithm called dual simplex, where it maintains this the dual feasibility, the second and third conditions, and it stops when you get a primal feasible point. Okay, so that is a dual simplex. And there are also the primal dual methods, which try to maintain the first two components. So at every step, you get a primal feasible x and a dual feasible y. And you stop when this complementary slackness holds. Okay, so those are the primal dual methods. So this is just to give you a flavor of what the various methods are. Of course, it may not be evident like in the simplex method how you got the dual feasible point. So it turns out there is a way that you can, I mean, directly from these steps that we did, it's possible to get the dual feasible solution also at each point. Sorry, not the dual feasible, this complementary slackness condition. So it will hold for some x and y, but not necessarily that y wouldn't have been a dual feasible point. But only at optimality you would have got dual feasibility. Okay. So I hope this is clear. Were there any questions on complementary slackness or on any of the example we did? Everything good? Yes, no? Bhavna, did you say something? Yes? Okay. Okay. Fine. Cool. Okay, so with this done, where we stopped last class was that, I did this example, okay, and where we got the primal solution using the dual optimum values. And I was trying to hint at the point where, what is the intuition of these dual variables themselves. Okay, so it gives some sense of, if you change the constraints of the problem slightly, how does the optimal objective change. Okay, so that's what I want to start explaining now. So this is the concept of shadow prices. Okay, so let's just take the same example, the one in red that you all solved graphically. Okay, so the problem was this. Let me just write it once more so that it's kind of clear. So you had min 3x1 plus 8x2 such that x1 minus 2x2 greater than or equal to 10, and 5x1 plus 8x2 greater than or equal to 2. And you had minus x1 greater than or equal to minus 15 and x1 greater than or equal to 0. Okay, so if you look at it graphically, so let me just draw this graphically, what it means. So you had this last constraint was x1 less than or equal to 15. So let this be 15. And so this was the line. So you wanted to look at this side. And then you had x1. So let me just also write the dual multipliers here. So this is y1, y2, y3. Okay. And so this corresponds to the third constraint. So I'll just label this as y3 for the time being. Okay, and x1 minus 2x2 greater than or equal to 10. So there we had something like this. So this is 10 and minus 5 here, right? So something like this. This was the first constraint, and we were interested in which side? This side. So 0, 0 is not part of it. So this side. And 5x1 plus 8x2 greater than or equal to 2. So here we had x1 is 2 by 5 and x2 is 1 by 4. Right? So something like this. And here also we were looking at this side. Right? So the feasible region was, this is what you all of you did in the midterm. Okay, so this is the feasible region. Okay. So the solution that we you got here was x1 star was 15, x2 star was minus 73 by 8, and the overall objective, let me call it z0. So this value was minus 28. So this is the objective, optimal objective. Okay, and yesterday we saw that for the dual, this was the optimal. Y1 star is 0, y2 star is 1, and y3 star is 2. So y1 star is 0, y2 star is 1, and y3 star is 2. Okay, so let me just write the constraints to which these correspond. So y3 corresponds to this one. Okay, and this corresponds to y1. y1 corresponds to the multiplier for this constraint, and y2 corresponds to the multiplier for this constraint. Okay, so one thing you see, like complementary slackness holds here, right? Because this is the point, the optimum point, and these are the two constraints that were in some sense active. Okay, by active I mean that they were satisfied with equality, and these were the two constraints which took a greater than 0 value. This other constraint, the first constraint was, it was not satisfied with equality. So there was a gap, and this was satisfied with a greater than sign. So that's why y1 star was 0. Okay. So now suppose you change, say the first constraint. Okay. So this y1, if you move it to, something like this. So if you change it by 1 unit, so x1 minus 2x2, if you made it greater than or equal to 9, okay, so even then the optimum is going to be just this, okay, because graphically if you see the direction of increase, so the gradient of this objective is something like this, it points in this way. Okay, so to minimize it, you have to go in this downward direction. So even if you change this constraint, the optimum is still going to remain as this point. Okay, so if you see the y1 star here is 0, so that is an effect of saying that it doesn't matter. Okay, so just keep that in mind, and let's just see what happens if you change the second constraint. Okay, so if y2, okay, the second constraint here, if you made it instead 5x1 plus 8x2 greater than or equal to 3, so new constraint is 5x1 plus 8x2 greater than or equal to 3. And suppose all other constraints remain the same. x1 minus 2x2 is greater than or equal to 10. And these all remain the same. Okay, so x1 greater than 0, and still the objective is minimize 3x1 plus 8x2. Okay, so suppose you're perturbing the problem a little bit so that only this constraint changes. Okay, so the new constraint is something like this, right? So so it would mean that x1 is at this point something like 3 by 5. Okay, so I think my drawing skills are quite bad. So 3 by 5 here, and this would be 3 by 8, so slightly higher. So maybe something like this. The new, okay. So the new constraint was this. Okay. Okay, so forget this line. So this was what I was talking if the first constraint changed. Okay, so okay, so this is the new constraint. So instead of this, you have this constraint. Now the optimum graphically, you can see that it's going to be this point. Okay, so again, it's going to be at the intersection of these two. I mean, it's as if these two become equalities, and that's going to be the new optimum point. Okay, so can someone tell me what's going to be the optimum value now? Are you here? Okay. There's something. Okay. So can someone tell me what's going to be the new optimum for this? It's the intersection of, again, these 2 points. I mean, the one in red and this x1 equal to 15. Guys, can someone say? I need some response. So minus 72 by 8 is which one? So
x2, and that's x1 is 15.
Okay, x2 is minus 72 by 8 and x1 is 15. Okay, so it's just you get it by substituting this value, right? x2 is 3 minus 5x1. So that would give you minus 72 by 8. So in terms of the optimal objective now, so z1, you're going to get 3x1 plus 8x2 still. Okay, so this is just going to be 45 minus 72, right? So this is what?
Minus 27.
Minus 27, right? Okay, so earlier this objective was minus 28 and now it became minus 27. So if you see the improvement or the change in objective is exactly this value of y2 star. Okay, it's y2 star is 1 and that's exactly the improvement that you get. Okay, so the key thing here is that this constraint changed. I mean, only the right hand side of this constraint changed. So you get a parallel line here, and the optimum also it's changed in such a way that the optimum is still at the same BFS in some sense. Okay, it's the intersection of these two constraints. Okay, these are the two ones which matter. And one thing to note here is that corresponding to this primal solution, the dual optimum, so y1 star for this new problem, the dual optimum is still going to be the same. So just compute, so the dual here, and for this problem, it's going to be, so the objective is the only thing which changes here. So that is maximize 3, so here, so this was y1, y2 and y3, right? So this is just, sorry. Okay, so this was just going to be maximize 10 by 1. Now, only this objective here changes, the right-hand side. So only this becomes 3 by 2 and minus 15 by 3. All other constraints remain the same, same as earlier. Okay, the constraints are the same as earlier, and only the objective is changed from 2y2. Okay, I haven't written it here. So yeah, from 2y2, it's just become 3y3. I mean 3y2. Okay, from 2y2, it just became 3y2. And if you look at the solution here, so the old solution itself, 3y2 star minus 15y3 star. So that is just going to give you 3 times 1 minus 15 times 2, which is 30, and that's minus 27. Okay, so the same value, which was feasible, I mean, which was optimum for the dual earlier, remained optimum for this new problem as well. Okay, but the only change was the objective improved. I mean, the x's of course improved, and that improved by a value equal to the y2 star. Now you can try the same thing for, if you change this third constraint. So this 15, right? X1 less than or equal to 15. Suppose you made it X1 less than or equal to 14. Okay, so this is one case. Now let's just write the other one. So min 3x1 plus 8x2, that's still the same. Subject to x1 minus 2x2 greater than or equal to 10. The second constraint is still the same. 5x1 plus 8x2 is greater than 2, greater than or equal to 2. Okay, because you want only one constraint to change at a time. So this one, suppose it became minus x1 is greater than or equal to minus 40. Okay. Now, so that would mean something like it became some other pen. Yeah. So it would be something like this, right? So this part, and it's basically all of this region. Okay. So the optimum is going to be this point. Okay. I hope this is clear, right? What I'm doing here. Please stop me if there are any questions. Okay. So now here, if you look at the optimum, it's again going to be at the optimum of these 2 points here. I mean, at the meeting point of these two, if they were equalities. So that would give x1 is 14. And what would x2 be? Can somebody tell me?
Minus 68 by 8.
Minus 68 by 8, right? So it's just 2 minus 5x1. That's going to give you minus 68 by 8. Let me just write it here. So 2 minus 5x1 by 8. Okay, so that gives you minus 68 by 8. And here, if you look at the objective, so let me call this now Z2. Okay, so Z2 is going to be 3 times 14. 14 into 3 minus, so minus 68, right? Plus 8 times this. So this would be what? What's the value you get? So 42,
minus
right?
16,
42.
minus 16.
Minus
26.
minus 26, right? Okay, so that's the value you get here. And so the original value Z0 was minus 28. And so Z0 minus Z2, if you take, that was going to give you, I mean, sorry, it's the other way, Z2 minus Z0. So the new objective minus Z0 was going to give you exactly 2. And this is equal to Y3 star, right? Okay, so you can verify that, here too, the same solution, y1, 0, I mean 0, 1, and 2. This is optimal for the dual of this problem as well. Okay, so in general, what happens is the dual objective values, right? I mean, the dual optimum values, the dual variables, that is telling you what is an improvement in the objective, or what is a change in objective if the constraint shifts by 1 unit. Okay, so let me just write it formally. So earlier you had that, C transpose X star was equal to B transpose Y star. Okay, now what you're doing is you're changing this B. So for the original problem, so it was, so the problem was this, right? Minimize C transpose X subject to AX greater than or equal to B. And what you're changing is the right hand side alone. So this B. So suppose you're changing BI. So the ith constraint, so Bi, that has become Bi plus some delta Bi, some small change. Okay. And so then if you look at the dual objective with Y star, what you're going to get is the original B transpose Y star. What was the original value? So let me call this Bi tilde. Okay. So the only change is in the ith constraint. All other right-hand sides are the same. So this B transpose, this B tilde transpose Y star is just B transpose Y star plus delta Bi times Yi star, right? So I'm just substituting the value of the dual objective here. Okay, and so this is the new change in the objective value. So this was in some sense what we got as one of the zi's. It's the new objective, so the perturbed objective for the perturbed problem. The perturbed problem. What am I writing? Objective for the perturbed problem. Okay, and this one B transpose Y star, this is the original problem. So this was Z naught. Okay, so what you're going to get is delta Bi Yi star is just Zi minus Z naught. Okay, and Yi star is just Zi minus Z naught by delta Bi. Okay, so this justifies the observation that we have been seeing, that the optimum dual value, it's just giving you the rate of change. So this is the change in objective if the constraint, if the ith constraint gets changed by 1 unit. If delta Bi is 1, what is the change in this objective? Okay, so that's why these optimum dual multipliers, these Yi stars, those are referred to as shadow prices. Okay, so in some sense, it's like the price that you are paying. I mean, if it's a minimization problem, it's the price for 1 unit change in the constraint. Okay, so this is useful in the sense, like, if you had a maximization problem. Okay, and in many cases, like in practice, you will have something like this, right? Maximize some things like some profit of some activities, of doing some activities, but there are some resource constraints. Okay, so something like aij xi is greater than or equal to maybe some limit of some resources that you have. Okay, so bj, so you have a lot of resources, but I mean, there's a constraint on the resources. Okay, so maybe it's a factory in which there's a limit on the number of machines you can use. Okay, so if you see something like this, now there'll be many constraints. At optimality, there will be some constraints which really matter. Okay, and that you can figure out by the values of the dual variables. Like here too, this constraint, this first constraint here, this doesn't matter, x1 minus 2x2 greater than or equal to 10. If you change it a little bit, it's not going to affect the objective. Okay, so here too you got y1 star 0, so that's what it means, that constraint is really not important. Okay, so same thing you will get in many problems in practice, that you will be able to identify the most important constraints. Now sometimes it could be that these dual values, they take a very large value. Okay, so something like if you have yi star is some 1000. Okay, so if you change this constraint, so the corresponding constraint, if you change by 1 unit, so if you are able to incur maybe just that many machines more, maybe just one machine more, you can make a profit of up to orders of 1000. Okay, so that's why this is important. This concept of shadow prices gets used. It has a very heavy economic interpretation. Instead of getting the new resource, and I mean, instead of resolving the problem, you're able to tell beforehand which one is going to help. And there's no point in improving the constraint, in getting resources for a constraint for which the shadow price is 0, right? So that's not going to anyway improve the objective, right? So that's the kind of interpretation that the shadow prices have. So I'll just pause for a minute. Are there any questions on this? Yes, no? No? Okay. Okay, I want to hear from some of the others as well. No, okay. So what about Rajneesh? Is it okay? No, okay. Okay.
Well, actually, for that y1 part, if we reduce
Yes.
it, we reduce it so much that it goes out of that feasible region. So are we checking it somewhere that we just change only that much so that this feasible region remains this one only? Like suppose
Yeah.
this y1 line,
Yeah.
just take it out of less than this point, this feasible point. I just take it less than this feasible point. So where are we checking that we remain in that region?
Yeah, right. So your point is valid. So in all these analysis, we are assuming that if you make a very small change, so that so that you remain within the feasible region, only then does all this analysis hold. Okay, if you're right. So if you change this constraint so much that you end up going out, and it could also be that the problem is infeasible. Okay, so that then all these things don't hold. So all this will hold only if it's a very small change, so that you still remain within the feasible region. And also, most importantly, this optimum point, right, which you get by the intersection of the two constraints, the original two constraints, that still remains the same. So it could be that if you change the constraint so much, maybe some other vertex starts becoming important. That's the optimal. Some new vertex becomes optimal. So in that case, this is not going to hold. Okay, so this is the idea of these is just if you change the problem very slightly, so that the feasible region doesn't change drastically, and your even optimum doesn't in terms of the meeting point, the vertex, it doesn't change drastically. Okay, so that is the purpose behind this analysis. Of course, if you change it very drastically, there's no other way, you have to solve the problem afresh. Or also, if you change like multiple constraints, right, if you, instead of changing just one constraint, if you changed two constraints, then also this analysis will not hold. You have to again repeat, or you have to find some other ways to do that. Okay, Rajneesh, it's answered.
Okay. Yes.
Okay. Okay, good. So, yeah. Okay, so if this part is clear, so what I would like to go to now is one example. It's another problem which you saw initially, the max flow problem. In the first class, I'd asked you guys to try to get some solution for this max flow problem. It was this oil delivery example that we had seen. So there was this oil network. Okay, and many of you tried. I mean, the idea was to send some flow from S to T. Okay, so that there were some capacity constraints, and you wanted to ensure that at every node there was this conservation. So you don't, if you send some quantity into this node A, exactly the same quantity goes out of this network, of this node. Okay, and in that way you wanted to ensure, and also you want to ensure that in each arc you don't send more than the capacity. Okay, and so with these constraints in place, you wanted to see what is the maximum that you can send from S to T. Okay, so this is a problem that there were many attempts that were made, and there's also this thing I told you about, this min cut, right? So you can keep making attempts, and so the way many of you did was you tried to keep getting better. You tried an initial solution, and then you try to propose a better solution, and that's the sort of approach we took. But the question was, how do we know that we are done, that there's still no better solution? And that's when we talked of this min cut. Okay, so we said that if you can find a flow, the amount of flow that matches some cut in the network. So if you're able to, so whatever you send has to, from S to T, has to cross the cut. Okay, has to cross a set of edges, so something like this, which divides the network into two. Okay, and this has to be true for every cut. You can cut the graph in various ways, so that S is on one side and T is on one side, and the maximum flow you send cannot exceed the value of every cut. Okay, so that's something we just quickly brushed over that time. So I just want to come back to this example, and in fact the one of the proofs for this is through duality. Okay, so have you seen max flow min cut? I mean, there were a lot of people at that point of time, so I just want to come back to this question again. So had you seen this in some other course, the max flow and min cut theorem? Yes, no? No? Okay. Not formally. Okay. Okay. So typically in algorithms, this is, I don't know whether you had seen the Ford-Fulkerson method of computing the flow. Is that something you saw in any course?
Yes, ma'am. We
You
saw
said
it in data structures and algorithms course.
yes, exactly. So, yeah, I would imagine you would have seen the focus in exactly that course. So it turns out that the basis for this algorithm comes from optimization and these concepts of duality. So I just wanted to touch upon this aspect. Okay, so let's just write the dual for the max flow problem. So if you remember, we formulated the max flow. I just gave you a formulation at that point. So where you say that you have your network is some G, which is made of vertices V and E. So edges E and vertices V. Okay, and the variables are the amount of flow that you send on each edge. Okay, and Cij is the capacity of each of the arcs. Okay, so you always want to ensure that Xij is less than or equal to Cij. So you don't exceed the capacity of each arc, and you also had this flow conservation. So at every vertex, you want to ensure that the incoming. So this is the summation of all xji for every node I. You take a node I, so xji denotes any incoming edge. So this is all the incoming arcs. Okay, the sum of incoming, and this is the sum of outgoing arcs. Okay, so the flow on the outgoing arcs. So this value, this difference is 0 for every vertex other than S and T. Okay, and for S you're going to have the usual assumption is that you don't have anything which is incoming. So you mostly have everything which is outgoing from S because it's a source, and so this difference between the incoming and outgoing, so this is the value minus V for I equals S. Okay, because yeah, okay, so this is the summation of all the outgoing things is V for S. So this negative of that is minus V. And for the terminal node, which is this one, the sum of all the incoming arcs, that is going to be exactly equal to V. Okay, and the usual assumption is that there is nothing outgoing from T. Okay, so that's why you have this kind of a formulation, and you want to maximize V. So it's either the value which is value of all the flow which is coming out from the source, or the value of all the flow which is coming into T. Okay, this is something that you want to maximize. Okay, so here the variables are both V and X. Okay, these are the variables, and X's are greater than or equal to 0, and V is unrestricted. So we can take either positive or negative values. Okay, so this is a max flow problem. So let's just try the dual of this. Okay, so can somebody tell me the dual? So I've just written the dual variables for benefit. So each of these, there are these constraints, this is a flow conservation constraint. So there are as many constraints as the number of vertices. Okay, so flow conservation. Okay, I think this is clear. So as many as a number of vertices, right? So for every vertex, you are going to have this constraint, and I'm going to call the multiplier for those as ui. Okay, and this xij less than or equal to cij, this is there for every ij. For every edge, you're going to have this. Okay, and all this also is for every ij mean. So, and with these we don't consider for the dual multipliers. So xij less than or equal to cij for every edge, and let me call the dual multiplier as wij. Okay, so can somebody tell me the dual? So first tell me like what should u and w, should it be greater than 0 or should it be unrestricted, or yeah, what is your sense of that?
You should be unrestricted.
Yes. So U is unrestricted. And what about W?
W should be greater than 0.
Yeah. So Wij is greater than or equal to 0 for all ij. Okay. So this we have. So now so just to make it a little easier, let's move these v's are also variables, right? So typically when we write the LP, we had that the right hand side was all constants. So what this is going to be is it's as if okay, so it will be minus v for I equals t. So that comes on this side. So there'll be a minus v here, and this will be a v here for I equals s. Okay, and here it will be 0 and 0. So I'm just writing it in small, in a lighter font. So can you tell me what is the dual? Tell me the objective. So is it a minimization? It's a maximization? What is it?
Minimize CIJ, WIJ.
Yes. So minimize summation ij. So for all the edges, you minimize Cij times Wij. Okay. Now the constraints. So let's start with maybe the easier constraint. So for v, so you take the coefficients of all the variables. So v and x's are the variables. So let's see what is going to be for v. Can somebody tell me? So v's come on this side. So corresponding to each constraint, there's a multiplier, right? So you need to sum up all the multipliers for each of these coefficients, wherever v comes. So can somebody tell me any attempts?
US minus UT.
Minus ut.
USP
Yes.
times USP.
Okay.
US,
So,
US minus VT.
yeah, US minus ut, right? So you won't have v in the dual because v is an it's the primal variable. So you only have the coefficients of that coming in the dual. Okay, so US minus ut, and so that is what you get. And what about, is it equal to 1, greater than 1? So 1 is from the objective here. So is it equal to, less than, greater than, what is it?
Greater than.
Greater than
0. I think.
So remember, v is there is no restriction on the values of v, right? So so v can become negative or positive, right? So remember, when you take the dual, you wanted if you have these variables are greater than 0, then it becomes inequalities. Then it's okay to put inequalities. But if the v becomes negative, then the inequality gets flipped, right? So that's why you need this to be exactly equal to 1. Okay, so ideally, yes, you would have US minus UT is greater than or equal to 1. If V was, if V was greater than or equal to 0, but since V is unrestricted, this is the only way in which you can get a valid upper bound to the original problem. Okay, I hope that's clear, right? Is it, who asked, who answered earlier? Was it Shivam?
Yes, ma'am.
Yeah. Is it clear, Shivam, like why we take equality?
Yes, ma'am.
Yes. Okay. Okay, cool. So this was the corresponding to V, what was the constraint. And now the harder thing, the seemingly complicated one. So Xij. So corresponding to Xij, what are the constraints? What are the multipliers that you will have? So directly one thing you can tell, right? Wij is going to come, right? Okay, so for every ij in E, so for every edge, okay, so we're writing this, the constraints corresponding to that. So corresponding to this constraint, you have Wij. Now you need to figure out what are the coefficients corresponding to this set of constraints, the flow conservation. Okay, so remember, this is there for every I. So for every vertex, you're going to have one constraint. Okay, so if you take the Xij in particular, the xij edge, I mean the edge xij, and you take xij value. So xij will show up in two constraints, one corresponding to vertex I and one corresponding to vertex j, right? So can you tell me, with this in mind, can you try to figure this out? So there's going to be, it'll be some UIs and some UJs, right? Because for corresponding to the I vertex I, you will get some UI, but it's a matter of figuring out whether it comes in the incoming or outgoing. So can you tell me what it would be? Anybody? Is it too hard?
When it's for I, the UI will be with the plus.
Plus sign.
Will be with But when it's for J, it will be a reverse. So maybe UI minus UJ.
So for J, so if you take arc IJ, right? So for the outgoing, so when it appears as an outgoing arc, so that would be for I, right? So xij, where it comes, when it comes as minus xij, so that would be for vertex I. So if you look at vertex I, all the incoming minus outgoing, and in the outgoing, you will have xij, right? So there'll be a minus sign corresponding to I. Okay, so it will be minus ui, okay, and corresponding to incoming. So if you look at vertex j, then xij is an incoming arc for vertex j. So then it comes in this first summation under that. Okay, so there you're going to have uj, so plus uj. Okay, I don't know if this is making sense to all of you. Are there questions? I can go over this again. So are there questions on how this constraint came? I mean, we still have to write the right hand side, but on this left hand side, is it clear or?
Yes, ma'am, it is clear.
It's clear? Okay. Okay, so now, okay, so what about this side inequality? Is it less than? Is it greater than? So the right hand side is 0. So for every edge, there's no xij terms coming in the objective. So this right hand side is going to be 0, right? So is it going to be less than, or is it going to be greater than, or what is it?
Greater than.
Greater than or equal to 0, right? Okay, so so this is the dual. Okay, so I hope the process of writing the dual is clear. So you have to do this a little slowly so that it's easy to make mistakes, especially these kind of constraints. So do it slowly and be relaxed. Don't get tense when you write the dual. That's a general tip. Okay, so with this in mind, let's just try to analyze the dual. Okay, so this was a max flow problem, and this is the dual of the problem. Okay, and so there's some observation, some analysis we'll do on this dual now. So first thing is, so let me just write one fact. So we will come to each of these facts. So the first fact is, so at optimality, there is going to be, so for the dual, the u star and w star, so that is the optimal values. So there exist so there exist u star and w star, all integer valued. Okay, so here we are not giving any constraints that u and w are integer valued, but it turns out that when you solve this problem, you will surely get an optimum. There is an optimum value, there's an optimum assignment of the variables which take only integer values. Okay, so this I will show this a little later, but take my word for it for now. Okay, so you can focus on the integer valued solutions instead. Okay, so now another fact. So if you take any cut, so this is actually what we are going to show is the dual is the min cut problem. It's going to solve the min cut problem. Okay, so I hope what a min cut is clear, right? I mean, are there any questions on what the cut problem is? Because you mentioned that you've not seen this theorem earlier, so I just want to get a sense. Do you understand what a cut refers to? Shivam?
Yes, maybe somewhat.
Yes. I didn't hear you. Can you?
I think I got somewhat on what is cut about.
Okay. So do you want me to just explain what a cut is?
It's the part where the flow is living
Okay.
where all the flow is living.
So, okay. So let me just tell you the idea of cuts once. Okay. So if you have a graph like this, so you have these source and terminal nodes, and you have some things going like all kind of edges and vertices and all that. Okay. So a cut is a set of edges. A cut set is a way in which you cut every path. Okay, so if you cut every path, so it's a collection of these edges such that if you cut them, these two nodes S and T are going to be on two sides. Okay, they are going to, it's like you're going to separate these two nodes and you're going to, disconnect the graph on these edges. You're going to remove these edges basically so that S and T remain, there's no connection between S and T. Okay, so the min cut problem is to find the cut of the least capacity. So all these, like in the graph that we have seen, all these have some capacities, right? So so the min cut says that what is the cut, what is the way to cut this graph so that the total you can think of it as a cost of the cut, so that is as low as possible. Okay, so this is the min cut problem and it has connections to the max flow. So the usual way to say is that there is a cut set of edges. Okay, so so this set of edges is a subset of E. Okay, and also this cut set induces two sets S. So it induces a set S and another set V minus S. So the idea is this set small s, the vertex, will be part of this set S and the T will be part of the other set. So basically all this on this side will correspond to the set S and everything on this side, so including this also, okay? So this whole thing will correspond to, it's the remaining parts, everything outside S. So if you tell this set of edges, that immediately tells you, it specifies a way to cut the graph. Okay, so that is what is the cut problem, and you want to find the best way to cut it, this with the lowest cost. So another cut is you can cut the graph like this. Okay, so then the new cut would be something, I mean, this would be the new cut, and corresponding to that, you will have this set and just this. So that is also another cut. So out of all these, what is the value of the min cut? Okay, so that is a cut problem. So I hope this is clear.
Yes,
Yes. Okay. Cool. So so now let's come back to here. So the claim is that this problem that we've written as the dual, that is going to solve the min cut problem. Okay. So the first fact is that all you can focus yourself on the integer valued solutions because the optimum is going to be integer valued. Okay. Now one fact I'm going to tell you is that you take any cut. So any possible cut, any cut set you take. So each cut set you take, that corresponds to a solution of that corresponds to a feasible solution. Okay. So to do this, to show this, I'm going to use this representation where see, I'm going to take ui. So yeah, so this ui is equal to 1 if I belongs to a set S and 0 if it doesn't. Okay, if not, if I is not in S. Okay, and immediately wij is equal to 1 if ij belongs to the cut set. So I'm going to refer to this cut set, the set of edges, as C, capital C, and it is 0 if ij, if the edge does not belong to the cut set. Okay, so I'm going to use, so if I have a solution like this, so this represents a cut, right? So the claim is that this cut, this assignment of u and w values satisfies all these constraints. Okay, so I hope the claim is clear what we're trying to say. Okay, so please ask if something is unclear. Okay, so now you can see that, it's just a matter of verifying whether all these conditions are true. Okay, so the first constraint tells you that us is going to be 1 plus ut. Okay, so let me just write it again. So us is going to be 1 plus ut. Okay, so usually by convention you will take the set S as containing this vertex S, and the remaining part contains T. So so what it means is US is 1 and UT is 0. Okay, so that satisfies these constraints. Okay, and now if you take this constraint, so Wij, let's just write it again. So for every edge you take ij in E, what you're going to have is Wij is greater than or equal to ui minus uj. Okay, and you also have Wij greater than or equal to 0. So I'm just writing these constraints from the problem. Okay, so if you have if you have any two elements of S, so if you take two elements of this set, okay, so that is specified by ui's, so ui equals 1 for everything in that set S. Now if you take this difference, you're going to get 0. So basically what it means is that these edges are going to take Wij equal to 0. So the reason is that, Wij will take a value greater than 0. It just needs to take a value greater than 0. And that is feasible here. Okay. So that's about the case when ui equal to uj. Now if, if, you take ui, so these edges if you take, okay, so ui is 1 and uj is 0 for these. So the Wij here should be greater than or equal to 1. So if you fix, so that it's also getting satisfied for these arcs which are part of the cut set. So this one is not in C, okay? So Wij is 1 if ij in C and 0 if it's not. So that also satisfies these constraints. So you can just check that it's true even for these arcs which are in V minus S. So these arcs which are completely contained here, the Wij is going to be 0 for those. And indeed, that's also feasible for this problem, for this dual. Is that clear to you? Are there any questions on this part? So it's already 11:30. I just want to go a little bit into this and wrap this up today. So yeah. So is this clear what I just said now? So any solution of this form is part of, it's feasible to the dual. Okay, all these constraints are satisfied by this kind of a assignment of u and w values. Okay, now even the other thing is to see that also if you take any feasible solution here, that also corresponds to a cut. Okay, so that's the third thing. So let me just write that. So fact 3 is any feasible solution corresponds to a cut set. Okay, so so the way to see this is, you have these constraints. So did I think I swapped the pages, but anyway. So okay, so any feasible solution is going to correspond to a cut set. The reason is that suppose it doesn't. Okay, so suppose there is, so the way I'm saying that it corresponds to a cut set is, I will say my C is going to be the set of all ij such that Wij is not equal to 0. So these Wij values, if you take any feasible solution, Wij's will be greater than or equal to 0. So now I'm just going to take the values of Wij which are not 0. Okay, and that I'm going to call as my cut set. So the and this, once you have this cut set, you immediately have this set S. Okay, it splits the two. So the claim is also that every path. So if you take some, so this is the network. Okay, you have all kind of paths going this way, and the claim is that, from every path, one edge will be part of this set C. So Wij will be greater than 0 for at least one edge from each path, for at least one edge from each path. Otherwise, it's not going to be a cut. Okay, so let's just see why this is true. Okay, so the constraint here you have is Wij is greater than or equal to Ui minus Uj. So let me just write that. Wij is greater than Ui minus Uj. And you have Us is equal to Ut plus 1. Okay, so this is true for all edges. So let's just see, suppose there is a path which has not been cut. Okay, so there is a path for which Wij is equal to 0 for all edges. So there's a path like this from S and so on up to T. Okay, and so this Us here is Ut plus 1. Okay, and for all these edges, Wij is 0 here. Okay, so Wij is 0 for this, Wij is 0. So none of these are belonging to the set C. Okay, so let us see whether that can happen. Okay, so now if this is Ut plus 1, right? So let's just take one possibility. So suppose Ut is 0 and Us is 1. So let this be 1. Okay, so this is 1 and this is 0. And you also have that Wij is 0. So what you have is Uj. So since Wij is 0, it means Uj is greater than or equal to Ui. So for this edge, for this vertex, the corresponding U is greater than this. So you can have something greater than 1 here. This will have something even greater. So maybe this will be 2, this will be 3, this is 4, like that. But finally, you want this T to take a value 0. Ut has to be 0. So that cannot happen based on these constraints, right? If all the Wijs are 0. So then, so that's why for sure you're going to have at least one edge for which Wij is not equal to 0. Okay, so is this idea clear? Are there any questions on this idea?
Ma'am,
Yes.
can we recap it once again? Like just a small recap.
This one on this third point?
No, ma'am, this idea, the last one.
This one. Okay, so about all the Wijs for every path, there'll be at least one edge, that one, right, Siddharth? Is that what you're asking?
Yes, ma'am.
Yeah. So suppose you consider that, Wij is equal to 0. Like there is a path. So what we're trying to say is that any path you take, any ST path, for every ST path you take, there'll be at least one edge. Okay, there'll be at least one edge in the path for which this Wij is greater than 0. Okay, so you will not have a case where you will not have a path where all Wijs are 0. Okay, so that's the claim. So, so to show that this is true, like assume that that's not the case. That means that there is a path for which there's an ST path for which every edge takes a value Wij equal to 0. Okay, so we are going to show that this will not happen, but assume that that happened. Wij is 0 for every of these edges on this path. Okay, so then what happens is because of the constraints. So this is also a feasible point. So remember that what we are starting off is from a feasible solution. So this is a feasible solution means there is a W and U such that they satisfy these constraints. Okay, so because they satisfy these constraints, it should be that Wij should be greater or equal to Ui minus Uj for all the edges. And you also have Us equals Ut plus 1. And of course, Wij is also greater than or equal to 0. Okay, so it satisfies these. Now let us check what happens if Wij is 0 for all these edges on this path. Okay, so because if we are saying Wij equal to 0, so take this edge and Wij is 0, so I is S here. But anyway, since Wij is 0, so in order to satisfy this constraint, Wij is greater than or equal to Ui minus Uj, you should have Uj is greater than or equal to Ui. Okay, so just substitute this inequality. Okay, and Ui here is Us. Okay, and because again US is ut plus 1 from the constraints of the dual. So from these constraints you have US is ut plus 1. Okay, so let's take an example like ut is 0 and US is 1. Okay, just to understand, I mean, just for simplicity, let's take this example. So then in this case, what it means is that this value uj has to be greater than or equal to us. So one possible value is, setting it to 2. It could even be 1. That's also fine. But anything greater than us. So that is what this will take. Okay. Now again for this edge, wij is 0. So here again you'll have uj is greater than or equal to ui. So here we got ui is 2. Now, because uj is greater than or equal to ui, this is also going to be something greater, right? Greater or equal to. Let's just take this as 2 itself. Okay, so uj is going to be 2. So this is vertex 3 and this is going to be 2. So like that, it's all, at every edge you cross with wij equal to 0, what you're going to get is on the j part, and from the incoming, like this is the I and this is j. For every j you get, the u value is going to be increasing. I mean, it's not going to decrease at all. Okay, so but on the end of this you will have ut, right? And ut has a value 0. Okay, so the whole idea was that us itself was greater than ut, greater than or equal to ut, and if you have every wij is equal to 0, there's no way you can reduce this value of us. I mean, you cannot make it 0 at any point. Okay, so that's the reason why this wij, if you take a feasible solution, it cannot be that there is a path where wij's are 0 for all edges. Okay, is it clear, Siddharth?
Yes, ma'am.
Okay, don't sound very convinced. Is it? Are there anything confusing you or anything bothering you?
No, ma'am. I'll just see it like after the lecture. I'll just see it once, like from the start, so it will be clear then.
Okay,
But right now it's clear.
it's
Yeah,
clear.
the
Okay.
explanation was clear.
Okay. Okay, so what we have here is now any feasible solution you take, you're going to get some cut set. So of course, we are just saying that we'll consider the cut as all these wij's which are not 0. Okay, but on the other hand, here we looked at wij is 1 or 0. But anyway, there is an interpretation of the cut that you're getting here. Now, in particular, you're trying to minimize this value. So this wij's, it turns out that it will have to be exactly equal to be 1. Okay, it cannot have something like wij's, like here we took it as greater than or equal to 0, greater than 0, but because you're trying to minimize for the optimum, you're going to have this to be minimized. So always the program will try to make this wij values as low as possible. Okay, so if it will try to make it so that if it is 0, it's even more identical, that's the lowest, it's more ideal, that's the lowest value it can take. But because of these constraints, it cannot set wij to be 0 for everything. It will set it to be non-zero only for a few, and that will exactly specify the cut set. Okay, and now you also have that it will not set it to fractional values. So once it cannot set it to fractional values for these wij's greater than 0, so the best value it can set is going to be 1, because you have that these are all going to be integer valued. Okay, so what I've shown is, suppose you take this fact for granted, then this is going to give you the solution of a min cut. Okay, and because of strong duality, you have that this max flow, I mean, these two, the primal and dual, take the same values. So that's why the max flow and the min cut are exactly the same. Okay, so I will just clarify this last point, this fact 1. I mean, it's a simple idea why it takes only integer values. Okay, so are there any questions up to this point apart from fact 1? Are there any questions? Okay, you're all very quiet. Okay, no questions. Okay, let me then finish about the first fact that all the solutions are going to be integer valued. So this has what is called total unimodularity. So let me just take it. So suppose you have a linear program, okay, and something like this: ax greater than or equal to b, x greater than 0. So we are not very particular at this point about the inequalities or whether it's a max or min form. So I'm just going to look at this matrix A, okay, the constraint coefficients that forms that you can write it as a matrix. So this matrix A is said to be totally unimodular. Okay, so when you say it's totally unimodular, what it means is that if every square submatrix you take, if every square submatrix of A has a determinant zero, 1, or -1. Okay, uh, so this seems like a little off track, but it means this is fact 1 for we're looking at fact 1's proof. So that's the definition of totally unimodular matrix. So any square submatrix you take here, this is going to have a determinant either 0, 1, or -1. Something here is going to be also satisfying. So it's true for every square submatrix. Now, if you remember a feasible region to an LP, we ultimately got it in this form, right? So AX equals B. I mean, you added slack or surplus or whatever. And finally, this was going to be the feasible region for the LP. And of course, you have X greater than or equal to 0. But if you look at this in terms of the basic feasible solutions, this in turn, like A, you could write it as some B and some N, right? And what this would mean is actually Bx equals B. So you remember that all the basic feasible solutions correspond to vertices, right? And each vertex you could construct by writing it in this way. So Bxb equals B. So x, you can divide it into xb and xn, and you had this form, right? Bxb equals B. And B is a full rank because it corresponds to a basis. It corresponds to a linearly independent set of columns of A, and this is full rank. Okay. Now, from your earlier, from your 12th standard classes, you would have seen that if you have this kind of a case, then what you have is XB. You can use Kramer's rule, right? So XB is going to be determinant of this matrix B, where the ith entry of xb is going so the ith entry of this xb vector is going to be as if you take this matrix B and the ith column you replace it with B. Okay, so the ith column you replace it with B, and the determinant of that divided by determinant of B. So do you remember this? This is something you probably have seen, right? Kramer's rule. Have you seen this earlier? Siddharth, you have a question? Yes? Okay. Okay, so this you remember from Kramer's rule, okay? So if you don't remember, just check it out. So when Kramer's rule says that you can do this. Now, what is going to happen is this is a square submatrix of A. So this is a submatrix of A, right? And so this is going to have determinant either 0, 1, or -1. Okay, but in particular, we assume that this was full rank. Okay, so then it cannot have a determinant of 0. So the only way is this has a determinant of 1 or -1. Okay, so any square submatrix you take of A, it is going to have this, provided A is totally unimodular. So that's what this means. So once this is exactly 1 or -1, now even in this part, the numerator is also going to be an integer, provided this B is also an integer, right? So that's why overall xbi is going to have only integer values. And of course, xn is 0. Okay. So what we are showing here is that if this constraint matrix is totally unimodular, then for every BFS you take, you're going to have integer valued solutions. Okay. And so the optimum is also one of these vertices, right? And so that optimum also is going to have, there is an optimum which has integer valued solutions. Of course, for an LP, the optimum, you can also have something which is not a corner point. I mean, there is for sure a corner point which is an optimum, but you can have something on one of the edges. So in that case, that won't be an integer point. That's fine. But the claim is there is at least one integer valued vertex which is an optimum. Okay, so yeah, so this is the proof of that. And so in this case, it turns out that, you know, for this min cut problem, if you take this constraint matrix and if you find all the sub determinants, all the square submatrices, and if you find the determinants, it turns out you're going to have the determinants of only 0, 1, or -1. So this, I leave it to you guys to check it out. Okay, and the right hand side is anyway integer valued, so that's why, you know, this fact is true, that, you know, there's going to be an extreme point which is integer valued. All the extreme points are integer valued, and so the optimum, there is an optimum which is integer valued. Okay, so I hope these ideas have been clear. Yeah, it is quite a lot of ideas to take in one go, but go over it slowly. So and feel free to ask if there are any questions. Okay, so I think with this, have I've told you what I wanted to talk to you about on LPs. Okay, so in the next class we will discuss constraint optimization. Okay, so the next class will, I think this Tuesday is a holiday, right? So we will meet on next Thursday at 10:30. Okay, so thanks. If there are no questions, you can leave, otherwise I'll hang back for a while. Okay.